Welcome back. So far, in our previous lectures of cache memory, we have only talked about reading of data. The CPU asks for data, the cache gives it. Simple. But today, we face a dangerous question. What happens when the CPU wants to change or write the data? Imagine we have a variable x is equal to 10. It lives in the main memory RAM, and we have a copy of it in the cache. Both say 10. Everyone is happy. Now, the CPU writes x is equal to 20. It updates the fast cache instantly, but the slow main memory still thinks x is equal to 10. We now have two different versions of the truth. The computer is effectively lying to itself. This is called data inconsistency, or a stale memory state. If another core tries to read from RAM right now, it gets the wrong answer. That is a disaster. So, we need a rule, a cache write policy. We have two main strategies to fix this. Write through, the honest, slow way, and write back, the lazy, fast way. Now remember one thing, that these two policies happen for cache hit situation. We'll talk about policies for cache miss later. So, now let's break them down. First, the safe approach, write through. Here, the philosophy is that never let memory be out of date, not even for a second. The rule of write-through method is that when the CPU writes data, write it to both the cache and the main memory at the same time, in parallel. Now, here is the hit workflow for write-through. The CPU sends the write command. The cache finds the correct line, assuming a hit, and updates its local data block. Now, the cache also forwards the write command to the main memory bus. So, the CPU must wait until the write is confirmed by both the fast cache and the slow main memory. Think of this like a bank deposit. You, the CPU, go to the bank and ask the depositor who is here, cache, to deposit 500 rupees. In a write-through system, the depositor doesn't just take your money and deposit. They pick up the phone, call the main vault manager in the basement, and wait for them to physically walk to the vault and update the master ledger. You are stuck standing at the window until that slow phone call is finished. The pro here is that its logic is simple to implement, and more importantly, the high consistency. The RAM is always completely up to date and so always 100% accurate. You never have to worry about stale data. This is great for multi-processor systems. And what is the con? Speed. Remember why we built the cache? To be fast. If we have to wait for RAM on every single write, we just threw away our speed advantage. Every time you save a file or update a loop counter, the CPU stalls. This massive write bottleneck creates massive traffic on the memory bus, slowing down the entire system, even including read misses. And it doesn't end here. To fix the CPU waiting problem, a small write buffer is often added, but this buffer can fill up quickly too, and the CPU will just end up waiting for the buffer. So much headache. So, engineers asked, is there a way to cheat? Can we be lazy now and do the main memory part later? Yes, and it is called the write back policy. So, let's look at this second strategy. This is what modern high-performance CPUs actually use. The philosophy here is that don't talk to the slow memory unless you absolutely have to. Just be lazy. Now, the rule of write back is, when the CPU writes data, we update only the cache. We do not tell the main memory yet. We let the memory stay stale and out of date. But wait, if the cache has the new value and RAM has the old value, how do we remember that RAM is wrong? We need a marker. This leads to a new piece of hardware that each and every cache line gets. This one extra bit on every cache line is called the dirty bit. Its logic is very simple. For a specific block, if dirty bit is 0, then the cache block is clean, which means that the block of cache is identical to that block in main memory. No change has been done. It is safe. But if the dirty bit is 1, then the cache block is dirty, which means it has been modified by the CPU and is different from main memory. It needs to be saved later. Now, let's quickly see the hit workflow for write back. In same way, the CPU sends the write command. So, the cache finds the correct line, which is a hit, and it updates its local data block. Then the cache just sets the dirty bit for that line to 1. That's it. The CPU is done. This is a nearly 1 nanosecond operation. Main memory is not even contacted. So, now, you must be thinking that, okay, this whole thing is alright, but when does the RAM get updated? The answer is only when that specific block is evicted to make room for new data. Now, before we throw the block away, the hardware checks the dirty bit. If it's dirty, then we pause and write the whole block back to main memory to save our changes. Then the new block can enter into cache. And if it's clean, then we simply just delete it. No need to save anything. Now, to understand why write-back policy is better than write-through, imagine a restaurant. Write-through is like paying for every single item separately. You order soup, you pay the cashier. You order bread, you pay the cashier. It's slow and annoying. Write-back is like opening a running tab. You order soup, the waiter adds it to your bill, here the dirty bit. Then, you order bread. The waiter updates the bill. You don't talk to the cashier at all. You only do the slow process of paying or the write-back at the very end when you leave the table. Okay, now let's see its pros quickly. Extremely fast writes. CPU writes are as fast as the cache, and it never waits for main memory. And consequently, the low memory traffic is the huge win. But on the other hand, write-back needs more complex hardware, as it requires the logic for dirty bits and the ability to perform a write-back cycle before a read-miss cycle. And also, the main memory is stale most of the time. This can be a major problem for multiprocessor systems, which need complex cache coherence protocols to manage it. Now, we have one final mystery. What happens if the CPU tries to write to an address that isn't in the cache? This is a write miss. We have two choices here, and they usually pair up with the policies we just learned. First, write-allocate. It is usually paired with write-back policy. The rule is that on a write miss, first fetch the block from memory and load it into the cache just exactly same as a read miss. And then perform the write operation on the now cached block. And what is the logic behind this action? The principle of spatial locality. If you wrote to it once, you'll probably write to it again. So we want the whole block in the cache. This converts future writes into fast write hits, maximizing the cache's speed, especially when write-back is used. Next, no-write-allocate or write-around. This is usually paired with write-through. Here the rule is that on a write miss, do not load the block into the cache. Bypass the cache and write the data directly to main memory. But why? To avoid unnecessary overhead and cache pollution. Since it is typically paired with write-through, the data must be written to main memory anyway. The rationale is to bypass the cache entirely, preventing the loading of a block that may only be written to once. This saves time on the initial block fetch and prevents a cache line from being evicted to make room for a block with low expected reuse. So, we're at the end of the video today. This is the summary of everything we've discussed so far. In a form of comparison table, you can quickly have an overview of this. So, here is the verdict. Write-through is simple and safe, but slow. It's like paying cash every time you order a dish in a restaurant. Write-back is complex and dirty, but incredibly fast. It's like using a credit card. Almost every modern CPU in your laptop or phone uses write-back. We chose speed over safety, but this creates a terrifying real-world danger. Since your CPU is using write-back, when you hit save on a document or reach a checkpoint in a game, the CPU might say done, but the data is actually just sitting in the cache. It hasn't reached the main memory or the hard disk yet. The dirty bit is 1. If the power goes out right now, poof, that data is gone forever. The main memory never got the memo. How pro engineers fix this? This is why data centers like Google or Facebook and banking servers use something called battery-backed write cache or BBWC. They put a literal battery on the memory controller card. If the power fails, that tiny battery keeps the cache alive just long enough to flush those dirty blocks to the disk. They use the speed of write-back but hack the hardware to get the safety of write-through. There is one more massive reason we use write-back, and it's inside your laptop right now. Your SSD. Since SSDs have a limited number of write cycles before they wear out, write-through would flood the drive with every minor change, high traffic, burning out the SSD quickly. Write-back acts as a filter. It holds many small writes in the cache, consolidates them, and only performs one large write to the SSD upon eviction. This drastically reduces wear and tear, prolonging the life of your storage hardware. So, the laziness of write back is actually what keeps your computer running for years. That is the beauty of this subject. We take a simple rule, don't write yet, and it ends up saving millions of dollars in hardware costs. So, it concludes today's video. If you liked it, share and subscribe. I'll see you in the next video.